pages 103 to 109. So, units for the rate of reaction. And the rate of reaction is expressed as the change in concentration over the change in time. There are several ways that concentration can be expressed, so the units for rate may vary. So you could have molarity per time, or molecules per liter per time, or grams per cubic centimeter per time, or molecules per cubic centimeter per time. So it's an amount per a unit of time. Seconds are usually the official unit of time, but other time units are often used as well. Now, the units for K, the rate constant, is never the same. It always changes dependent on the order of the reaction. So rate is always the same units, and in the brackets it's always the same unit, but it depends on what power is that unit raised to really dictate what the rate constant's unit would be. So example 14.35, find the units for the rate constant K for this rate law, and note that A in brackets indicates units of concentration, which is moles per liter or molarity. So first, I'm going to go ahead and tell you that molarity is the same thing as saying moles per liter, which is the same thing as saying moles times liters to the -1. Okay, so with that said, we have this equation right here. The rate equals the rate constant times A raised to the first order. Rate is always the same unit, molarity per second, equals, K is what we don't know, times, in your brackets, it's always molarity raised to this power. So since we have molarity to the first power, it's going to be just molarity. What I want to solve for is K. So what I'll do is multiply both sides of the equation by 1 over m. This will cancel out molarity on this side, and over here what happens is the molarity also cancels, and so what you're left with is 1 over s is equal to the rate constant, which is the same thing as saying s to the -1. And so that would be the unit of K in this example. Example 14.36, find the units for the rate constant K for this rate law. So we have rate is now equal to the rate constant times A raised to the second order. And so remember, rate is always going to be molarities per seconds, not always, but for now, concentration will be molarity per second, equals K, the rate constant, times, and the unit for the A is molarity, and it's raised to the second power, so we have molarity squared. So the goal here is to rearrange this to solve for K. So what I'll do is multiply both sides of the equation by 1 over m squared. That'll cancel out this, and that leaves me with K equals, notice here I have molarity in the numerator and molarity squared in the denominator, and you see how it's being multiplied? So it's essentially like this. And this molarity is going to cancel with one of these two, leaving me with just one molarity in the denominator and seconds in the denominator. So what I have left is 1 over molarity times second. This is the same thing, so let's write this in a few ways. K is equal to 1 over molarity seconds, or molarity to the -1 times second to the -1, or, this is the more complicated way to do this, remember molarity is moles per liter. So if I take the inverse of that, then what I have here is actually liters per mole. And so I could also say that we have mole to the -1 times liter times second to the -1. And so there are 3 ways to answer this question. Now we're going to determine the reaction orders from experimental data. So here, recognize that anytime you want to know the order of a reaction, experimental data can be used to figure that out. In these problems, the initial rate of reaction is measured with different starting amounts of reactants. The effect of the concentrations on the rates of reaction are then used to determine the order of reaction. Determine the order means use the data to find the exponents n and m in the rate law expression. So now we'll work out a sample problem. So example 14.37, determine the order of the reaction and the rate constant K for this reaction, A plus B yields C. So let's just go ahead and kind of scribble out what the rate law is going to look like first for this. We'll have the rate is equal to K, the rate constant, times the concentration of A times the concentration of B, where A is raised to the mth order and B is raised to the nth order. So we're actually going to use this experimental data to help us figure out these two values, the orders of A and B. So how do we do this? Well, first of all, notice that you're given 3 data points for this experiment, experiment 1, 2, and 3. And you're given the concentration of A in each experiment, the concentration of B, and the initial rates. So what I want to do is notice that experiments 1 and 2 have the same value for A. And so what that means is A is constant between experiments 1 and 2. It's not changing. And so what I can do is use the data for B and the initial rate for experiments 1 and 2. Since A is not changing, then the information that I calculate will tell me what the order of B is. So I'm going to take the greater value, which is 0.2, and put it over the lesser of the two values, 0.1, equals, and then I'm going to put the rate, 4.0 times 10 to the negative 5, over 4.0 times 10 to the negative 5. Now, this is B, the concentration of B, and so this raised to the nth power is going to tell me the order for B. So 0.2 divided by 0.1 gives us basically 2 raised to the nth power is equal to, and this divides out to be equal to 1. So what could n be in order for 2 to the n to equal 1? Well, it would have to be 0 because any number raised to the power of 0 is equal to 1. And so n is equal to 0, which is the order for B. So now we know rate equals K times A, and B is to the 0 order. Okay, now let's figure out what the order is for A. So I need to pick 2 experiments where B is not changing, in this case experiment 1 and experiment 3. So now I'll look over here, and between 1 and 3, 0.2 is the greater value, so I'll put 0.2 over 0.1, so it's experiment 3 over experiment 1. And that is going to be raised to the mth power, the order that we don't know for A, is equal to, and then take the rate in experiment 3, 1.6 times 10 to the negative 4, and divide it by the rate in experiment 1, 4.0 times 10 to the negative 5. When you simplify this, we're going to get 2 to the mth power is equal to, and when I divide these out, I get roughly 4. So 2 raised to what power is equal to 4? Well, hopefully it's obvious that 2 squared is going to equal 4. Therefore, m is equal to 2. So A is at the second order. So I'm going to put a 2 here for letter A. So now we've actually managed to determine the orders of both of our reactants. Now the question is, what is the value of K? And so what we'll do is substitute the values from one of the experiments into this equation and then solve it for K. So I'm just going to choose experiment 1. where the rate in experiment 1 is 4.0 times 10 to the negative 5. And remember that the rate is in molarity per second, equals, I do not know what K is. A in experiment 1 has a value of 0.1, and it's raised to the second order, so it's going to be 0.1 squared. And then really, because B is raised to the 0 order, I can just leave it out, because anything raised to the 0 order is just going to equal 1, and so it's really not going to affect this math. So now I'm going to divide both sides by 0.1 squared, keeping in mind that 0.1 is in a unit of molarity, which means that when I square that, I have molarity squared. So this down here is molarity squared. So K is equal to, when you divide 4.0 times 10 to the negative 5 by 0.1 squared, you get 4.0 times 10 to the negative 3. But here's the kicker. What is the unit for this? And so when you take molarity per second divided by molarity squared, this molarity cancels with one of these two, and I'm left with 1 over molarity times second, which is the same thing as 4.0 times 10 to the negative 3, molarity to the negative 1, seconds to the negative 1. A final little note at the bottom of page 108 and at the top of page 109. Suppose the problem used words like these to describe the rate varied with concentration. The rate of reaction increases by 4 times when the concentration of A doubles. Those words can be translated into mathematics to give this equation, that your rate increased by 4 times, and this is when A doubles, and so the question is, what is the order of A? And then, of course, 2 squared equals 4, so the n must be equal to 2. So this is just another way that you might see the wording in your Moodle quizzes. So pause the video and copy down the following notes. Here's a little note card for you. Brackets are going to stand for concentration, which is always in a unit of molarity. Rate has units of molarities per second, which could be written molarity times second to the negative 1, or moles per liter to the negative 1 times seconds to the negative 1. If you are dealing with the rate for gases, then you're going to deal with pressure. And so the units are going to be atmospheres per second, or atmospheres times seconds to the negative 1. K is the rate constant. The units for K are going to vary depending on what the order of the reaction is. So you'll always have to mathematically determine what is the unit for K. And finally, orders of reactions can always be determined through calculation using experimental data. So all the other ways that we've used up until now to figure out orders of reactions were just simple ways that we'd get lucky and be able to tell with stoichiometry or knowing the slow versus fast steps. However, no matter what, the orders can always be figured out by experimental data.